you basically kind of oscillate when you try to do something. And so if you remember, the Parkinsonian tremor is a resting tremor that goes away when you actually try to do something. Well, somebody that has cerebellar disease, they get a tremor, they start shaking whenever they do something. So if you maybe pick up the root beer can, I'd be shaking while I pick up the root beer can, but then when I get still, I don't have any tremor at all. So Parkinsonian tremor, resting tremor, cerebellar tremor is an intention tremor. It's when you do something. Along with that, the eyes wiggle. When you get wiggly eyes, you get what's called nystagmus. So if you look at somebody, instead of them looking right at you, their eyes are beating, they're moving constantly. That's called nystagmus. Because you're weak on that same side, typically you tend to fall to that side, same side if you have the weakness. You may have a decomposition of movement, so instead of something being very smooth, you may have trouble kind of getting there because you have to think about it, your brain's having to work, you can't use the subprogram anymore. Dysmetria is very, very diagnostic for cerebellar problems, and so let me get a volunteer. You can stay there. Oh, that's right. Stand up. Okay. The way we test for this is to do the finger to nose test, where you do like this. So I want you to take your right hand, touch my finger, and then touch your nose. As fast as you can. As fast as you can. Okay. And so you test one, okay, then you do the other side. You have to test both sides, right? Because it could be that it's just one side. Okay. So he's really good. I mean, it's really very normal. Now, you're the doctor and I'm the patient. Okay, so now I've got a cerebellar problem. Okay, so I want you to show me where I'm going to point. Okay, you know exactly what I did. Okay, so I do my nose. Okay, and now instead of I'll go past it like this. Like that. I can't hit it. And I go past. See how I miss it? I can't go, and I'll wiggle as I go towards it. So this is a way a cerebellar patient would do this test. Okay? And that's called past pointing. So you overshoot. The motor system overshoots. No, you're not done yet. No, it's okay. So the other one is called dysdiadochokinesia. You know all about that.
Oh, I'm sure I do.
So dysdiadochokinesia is an absence of being able to do rapid alternating movements. And the best way to test this is just to have you do an alternating movement like this. Fast as you can. Very fast. Good. Great. Now do the other one. Okay. Very good. That's how you test for dysdiadochokinesia. Now if I have cerebellar lesion on my left side, what I'll do is I'll do like this. I can't do the rapid alternating movements. Okay? That's called dysdiadochokinesia. Thank you. Very good. So one other problem that cerebellar patients get is scattered speech. They have explosive speech that is not very rhythmic. Okay? That's called scanning speech. So it's kind of like you have an ataxia, except it's kind of an ataxia with your vocal system. Okay? So how do you test cerebellar problems? You make somebody move. That's how you would do the test. So you have to also be certain that all of the other motor systems are okay. Because you can have defects if you have a corticospinal lesion or if you have some proprioception. If you have, for example, some problem, with the posterior columns, you can't perform these either. So you have to be certain. Basically, you have to test to make sure that the efferents and afferents are all okay. You go back and look at the diagram that kind of shows, all of the things that kind of bring information into the cerebellum. And so you have to test both extremities. You can't just do one side or the other. Just doing one side, you'll miss half of the disease. So you need to always do the test for the rapid alternating movements. so you also need to know that acute cerebellar pathology, for example, if you have an acute stroke, you're going to have a lot more symptoms than if you have a slow-growing tumor. What happens typically is if you have a slow-growing lesion, you have time to compensate, and so your function is actually much better than what it would be if you had something that happened very suddenly, very quick. You can also test, one of the other things you have to also be sure is that you don't have something that's, a brain tumor or something in the frontal lobes, because that then can press on the postcentral gyrus and give you some cardiospinal, kinds of symptoms that would mask something that you might pick up that would be cerebellum. And so it's a good idea to also do a little test like, well, what day is it today? And if they say it's December the 1st, then probably they got some problems. Or who's the president of the United States? And if they say George W. Bush, well, then you probably are in trouble. So basically, you've got to kind of do a little mental test, to kind of tell that somebody's kind of with it. Okay, so what kinds of problems do you get? Hemorrhages, for example, hypertension can cause a hemorrhage in the lateral hemisphere of the cerebellum. Adults, typically tumors are metastatic, and so in adults, the kinds of tumors that you would see would be prostate tumors in men, breast cancer in women, lung cancer in both, GI tract lesions in both men and women. Interestingly, children have a propensity to have disease of the cerebellum. So children get cerebellar pathology more so than adults. And the reason is because the cerebellum is still differentiating, it's still learning, it's still growing. And so some of the kinds of things that can affect the cerebellum in children are astrocytomas, which is a tumor of the astrocytes, medulloblastoma, which is a primary kind of a precursor cell for the medullary cells in your brain. Hemangioblastoma is another common one. So hemangioblastoma is typical in von Hippel-Lindau syndrome, which is also associated with Port-Weinstein. And so, those are the kinds of things that you can see with cerebellar pathology. Now, there is one other thing that's kind of interesting. I have a friend down, this fellow teaches at the University of Texas Health Science Center at San Antonio, and he has some interesting thoughts about the cerebellum too. If you remember the timing diagram that I showed you the last time, then you've got those climbing fibers, which are the clock that are sending pulses up to the cortex, kind of get timing for all your motors, so when you're doing something, they're firing a lot. Well, it turns out that sensory information is gated. It has to have some timing too. There's a timing aspect to all of our sensory information. And so he came up with this little test where you kind of have a patient test whether they can feel sandpaper that's coarse or fine. And if you restrict the hands and you don't ask them to differentiate, there's not much that you see on the functional MRI scan. If you have to differentiate, you have to say, well, is it coarse or if it's coarse or fine sandpaper, as shown here in B, then there's a little more activity. But the very most activity you actually get is if you have somebody that just has a bag of marbles that's one's coarse and the other one's fine, and you go in and you have to feel the texture and you have to actually sample. So you're actually actively sampling. When you're sampling, you're sending a bunch of information up the proprioception system, and some of this is getting into the cerebellum. And so the cerebellum, we know from these kinds of studies, is not only motor, but it's probably very important in our sensory timing, in our search movements that we use to actually do proprioception. So again, if you don't move, for example, if you pick something up and just hold it, you can't tell what it is. You actually have to do active exploration. You actually have to move it around. And so that involves both sensory perception and movement in terms of trying to interrogate your environment. And that's what D shows us there in that diagram. The cerebellum becomes very active when you do an active sensory discrimination that involves motor and feeling. Okay, so cerebellum, probably has some other functions than just motor. Any questions about cerebellum? Now, I told you before that the cerebellum is like a big negative feedback loop, okay? And so you can probably think of a lot of other systems that provide homeostasis that are also big negative feedback loops that kind of keep us in our homeostatic equilibrium. So, I mean, can y'all give me a few thoughts? What are some of the things that are big homeostatic feedback control systems? Glucose, I heard that.
Body temperature.
Blood pressure.
Body temperature.
Body temperature.
Blood volume.
Blood volume, yeah, probably so.
Body.
Everything that involves the hypothalamus, which we'll look at next or the next time, all involves big negative feedback loops. In fact, there are some really good textbooks that are written that just describe biological control systems. And you can, analyze these by taking data, and I'll hopefully show you a few things that we can measure with the cerebellum today that will actually allow us to write equations that describe the way that they work, okay? And so we can use our control theory, our control knowledge, feedback systems, to analyze these biological control systems. Okay. So, there are three things. That these control negative feedback systems do that are very, very important, and just in terms of the way it kind of controls the way our body works. And if you throw these out, if you disrupt them in any way, then you get instabilities. And some of these instabilities that we just talked about with the cerebellum, like the past pointing, and the inability to do the rapid alternating movement, you can absolutely describe these mathematically using control theory. So the basic idea goes back to this negative feedback system where I have some kind of a feed-forward system, which is called the plant, and then I have some sensory system which checks the output and then sends a little piece of it back up here to compare with your set point. So basically I'm looking at where I want to be, where I am, and then close the loop, and it will direct you to that appropriate action in a very stable way. Now, if you go through, you just look at the math there that I did. Turns out that what we call the closed loop gain function is K over 1 plus KH. Okay, that's the closed loop. Y'all probably take systems, right? Y'all seen this before, right? Okay. It can also be rewritten, a lot of times we write it as K G of S 1 plus K G of S H of S. Okay, that's another way we write it. So the kind of cool thing is that if you allow the feed-forward gain K, that's the gain right here, if you let this get very, very big, if it gets really, really big, okay, it turns out that if you look at that K over 1 plus KH, as K gets very, very large, the 1 becomes insignificant, and so you get K over KH, and so basically the limit as K gets very, very large is your closed loop gain goes to 1 over H. And so if you have a very stable feedback system, if you have a very stable sensory system, it makes the whole system be frequency independent. Let me say that again, that's important. If you have a very stable sensory feedback system, the whole closed loop becomes stable because it becomes frequency independent. All your frequency information is in the G of S, okay? And as K gets very, very large and it goes to 1 over H, if H is frequency independent, then the whole system becomes frequency independent. So, being kind of simplistic, I like to look at 3 big advantages of negative feedback. One is feedback stabilizes gain. And so if you look at how much the closed loop gain changes as a percentage, so that's delta closed loop gain divided by closed loop gain. And delta K is open loop gain divided by its value. So this would be a percent change in closed loop gain. This is the percent change in open loop gain, okay? Turns out that open loop change gain and stability is reduced by that 1 divided by 1 plus KH. So you basically are able to reduce that by that factor of 1 divided by 1 plus KH. Okay? And the proof of that I went through here. So basically you just take the derivative of closed loop gain with respect to K, and you do the math, and basically you get what I just wrote down for you. Okay, you all can look at that on your own. So as an example of this, in terms of gain stability, the question is, how large must the gain be, K, feed-forward gain, to ensure that a 100% change in K, change it by 100%, only results in a 0.1% change in closed loop gain. And so, you take your 0.1, of course that's a percentage, so that becomes 0.001 equals 1 divided by 1 over KH. I told you what H is here. And this is 100%, in other words, 100% change in K. That's that dk over K. And if you just plug the numbers in, I think you'll find that K is about 10 to the 4th. So that tells you the minimum value. Now, if K is larger than that, the gain is even more stable. And so that kind of tells you that the more feed-forward gain that I can put into the system, then the more stable the gain will become. And this is important because if you have gain instability issues, then the whole closed-loop system becomes less reliable. That's number one. Number two, negative feedback reduces distortion. So here I have my negative feedback system with my feed-forward gain. And actually, I've made this plus here because I use this as a minus K in the feed-forward gain. Basically, it's the same thing we just did. And I'm adding distortion here, just adding it. So basically, when I get to this point, E out, I've got basically H times E out plus ES times K, and then I add the distortion. So basically, I've added the distortion. And so it turns out that when you do the math here, you still have your equation that actually describes the gain. It's still a negative feedback system, but you reduce your distortion by 1 over KH, just like we increase the stability. And here's the proof of that. I just went ahead and wrote that down. And so, again, you get this huge distortion reduction. And actually, this was a trick that was worth hundreds and hundreds of billions of dollars. I mean, when they first figured this out, that a long time ago, people used to spend, many dollars trying to build amplifiers, for example, that were low harmonic distortion amplifiers. And it turns out that you can take a very simple little linear gain element, it's basically a 740 C op amp, and you can, because it has a gain of 10 to the 6th, you don't have to worry about the distortion, because if you actually plug it in, make a reasonable kind of an amplifier, you're going to reduce this distortion by this 1 plus KH. So as long as you have a large enough K, you can end up decreasing the distortion to whatever level you want. And so it was a trick that it's used today. It's in your cell phone, it's in your home amplifier, your TV, everything. It uses the same little trick to decrease distortion. The third thing that this does is these negative feedback loops improve the frequency response. And so, we always talk about bandwidth, more bandwidth. So, if you now, I included the frequency information, so I have kg of S instead of just K, but it turns out that it still works the same way. If I make K big enough, my closed loop gain just still is that 1 over H. It's basically the inverse of the negative feedback loop, the sensory information. And so all I have to do is to make something frequency independent is to make H independent of frequency. So if I make H of S be equal to some constant independent of frequency, then the gain becomes independent frequency. I can basically get infinite bandwidth. Okay, it's a beautiful trick. I'll show you how it works here. Here's an example. Here's a feed-forward system. So I have a plant function here of 10 to the 7th over s plus 10 to the 3. And here I have a negative feedback h that I set as a constant. It's not dependent upon frequency. Okay? And so, again, you can just, the closed loop, when I close the loop here, my gain function goes from 10 to the 7th over s plus 10 to the 3rd. If I break this wire here, my gain is this number here. But as soon as I put this negative feedback in, I have to close the loop and figure out what it is. So it turns out that the closed loop gain function, is like 10 to the 7th over s plus 10 to the 5th. Okay? Now, if you do a Bode plot, y'all know how to do Bode plots, right? So the Bode plot is 20 log to the base 10 of the amplitude, right? So on this axis, I'm plotting 20 log to the base 10 of this number. And on this axis, I usually do the radian frequency omega, and omega is equal to 2 pi f. And so this is 20 log to the base 10 of the amplitude. And so when I do a Bode plot of the first one, so if I do the open loop gain function, so the open loop gain function G open is just this guy here. And if I plot that gain function, it turns out that when you look at this, start first by just looking at what the low frequency gain is. And so if you look and if S goes to 0, so if this number goes down to 0, I end up with 10 to the 7th, or 10 to the 7th over 10 to the 3. So that's going to be 10 to the 4th. Okay? And so 10 to the 4th, 20 log to the base 10, or 10 to the 4th is going to be 80 dB. This is 80 dB. Okay? And so if you also look here, the break frequency for this, so j omega plus 10 to the 3, that's going to break at omega equals 10 to the 3. So my actual function is going to look like this. And it's going to be down minus 3 dB here. Okay? Now, that's open loop. Now, when I close the loop, my gain function becomes this guy right here. And so, again, when you look at low frequency, let this go to 0. It's going to be 10 to the 7th over 10 to the 5th. It's going to be 10 to the 2. And so that's going to be 20 log to the base 10 of 10 to the 2 should be about 40 dB. Okay. It's going to stay 40 dB all the way out until you get to that break frequency. Okay, and the break frequency is going to be j omega plus 10 to the 5th. So at omega 10 to the 5th here, we're going to be down minus 3 dB. Okay, so the point here is that I can increase the bandwidth ad infinitum just by increasing the amount of feedback in my feedback loop. So that's a pretty cool trick. We'll study that in systems class. So we use that with feedback amplifiers. Here's an example of a non-inverting amplifier. And we know, probably memorize the gain function is 1 plus R feedback over Ri. You can prove that just by using the same formula we just did. Basically just plug the numbers in. Here, your H function is just going to be a resistor divider. It's going to be Ri over Rf plus Ri. That's the H function for those two resistors, right? That's the voltage divider. And then the gain, basically, for K very large, and K infinite, is 1 over H, and that's going to be R feedback over Ri plus 1. So basically, all you have to do is know that formula for K over 1 plus KH. Isn't that cool? Okay. So, again, you can use this to analyze, this would be an inverting amplifier. basically for the inverting amplifier, gain function is just going to be R feedback over Ri. But more importantly, we can use this to characterize, we basically use the same theory to characterize the systems that we're studying. Okay? So, I'm going to give you an example here that we'll kind of work in class. And so, if I'm going to test the cerebellum, what do I have to do? I like to pick on you. You're somebody. How do you know to test the cerebellum?
Give it an input and see what it does.
What the output is? That's good. So you can calculate the transfer function if you know input. So basically output or input gives you your transfer function. Okay, but specifically, if I want to know the closed loop transfer function for my cerebellum, how do I test it? Why would I want to do that? Is that something important, or is that just something silly for 365R? Is there any reason I'd ever want to know how good somebody's cerebellum works?
Well, there's nothing wrong with it. It get worse.
Could get worse. I mean, there's certain kinds of things that we do that are possibly dangerous that you know, we want to know that somebody's qualified, right? To fly an airplane, maybe, or to drive a train, or to drive a car. Okay? I like that answer. Driving a car is really dangerous. It requires skill. You go around with your cell phone, you know, time you're diluting your sensory input, and get distracted, and you have a crash and kill somebody. But anyway, how do we test? So, you got a driver's license, right? So when you got your driver's license, did you have to do anything special? Did they test your cerebellum?
Into a vision test.
Well, that's not. Well, it's good to do a vision test. It's good to be able to see.
No, they didn't.
They didn't specifically. Did they do the finger to nose and the rapid alternate? They didn't do that, did they? No. Okay. I think that's important. Should they?
Yeah.
Yeah. Really what?
Older people maybe not.
You're discriminating against me.
Grandmas are bad drivers.
But I'm gonna drive.
Well, older. You look young.
How? So when do you start doing this? About 80?
5.
Okay. That's after all the old people are dead, right?
That's like the really old people.
Really old people. Okay. Well, as a matter of fact, driving skill, we know, deteriorates as you get older. This is actually a real good question. And in fact, the Texas Department of Public Safety came to our lab and asked us to devise a test for testing cerebellar function. That's something that we biomedical engineers do. So, you know, if they're going to give us money, we're going to do the test, right? So we come up with a test. Now, what kind of test do we want to come up with? How are we going to test? How are we going to make an objective test where I can write an equation that describes your cerebellum? What do I have to do? I have to make you do something, right? I have to make you do some skilled motor function, right? That's what we just talked about. You have to do something. So what kind of a thing might I do?
The nose test.
Finger to nose, that would be one thing. That's kind of hard to quantify. What else? Some kind of maybe a tracking task or a pointing task?
Yeah.
Do you think about that? So maybe like if I had a computer screen maybe, and I had a dot, and I said, you keep your finger on the dot. What do you think about that? Maybe that might be something, maybe. So if you have a cerebellum problem, what are you going to do? You're going to move around. You're not going to be able to follow the dot, right? Okay. So let's think for a minute. So I can come up with a test where, for example, I can just do a quick step function, right? Okay. Now the Fourier transform of a step function. 1 over S. That's right. Okay. So all I have to do is to have a dot on the screen, and I tell you keep your finger on the dot. So I pop it up here, and I see how good you tracked it. If you go up here and do like that, that's going to be different than if you did like that, if you just came up and stayed real close. Turns out that, so you can, irregardless, I mean, you can do another tracking task, would just be have the dot make a sine wave. dot goes up and down. You just have to keep your finger on the dot. Okay? What's the Fourier transform of sine function?
Discrete.
Continuous time. What do you think about that? Anyway, so, irregardless of whatever, I can characterize the input and I can measure the output, right? Okay. So if I want to describe the system function now, the system function now in this task involves my eyes, my proprioception system, and my motor system. So remember, the cerebellum acts like a great big what? Comparator. So in our diagram, the cerebellum is actually that element which compares the proprioception and visual input to the desired function to give me an error signal. Okay, we know that's the way it works. And so actually we did this. Excuse me, we came up with this test, and it was, we did it on a computer screen, and basically we had subjects that just had to follow the dot, you know, with their finger, push the test both sides. And so somebody like you guys, when we did this, you could track so I'm going to plot here the closed loop function. Closed loop function went something like this. It dropped off fairly quickly. But the break frequency here was at about meg equals 10. So the frequency was about 6.8. So roughly 2 hertz. Okay. So I do the test, and so this is kind of normal. And I'm going to tell you that this drops at minus 40 dB per decade. Now, I want for you to write me the closed loop transfer function. Anybody want to write that down? Okay. So what does 40 dB per decade tell you? Is it 1 pole or 2 poles? 2. Okay. And S plus 10. Right. And to make it 0 gain, in other words, you could track it perfectly for just very slow movements. We have to do what? Put 100 up here. So that's the closed loop gain function. Okay? That's normal. Now, if you take grandma or grandpa, what do you think happens? Well, we did that, and we tested, and sure enough, I'll do this kind of wiggly so you can kind of see what it looks like. This gain function goes down like this. The break point here is at 1. So what is that? Closed loop function. If I have 60 dB per decade roughly, that tells me I have 3 poles, right? So I'm going to have S plus 1. Okay. So we can look at grandpa, and this is young adult. And so we can actually put an equation that describes. We can actually do this little test. It only takes about 5 minutes, and we can pretty much describe your motor function. That's powerful. I mean, as biomedical engineers, we know how to quantify, measure, quantify, write down, model. Yes?
How exactly did you get the 100 in there?
No, because when this is 0, when this is like way over here, the gain has to be 1, So 100 divided by 10 squared is 1.
So for the right, it would have to be like house. If it goes to the third, it'd have to be 1,000.
Here,
Or
1 squared is, 1 cubed is still 1.
no, I mean like at the top of the cube.
Here,
Yeah.
I'm sorry, I don't understand the question.
Like if that one were cube instead of square.
Oh, if it was a
1,000.
cube, yeah, it'd be 1,000.
It's just whatever to match that.
Yeah, I mean, so you have to get the game right at DC.
Okay.
That just compensates for DC. Okay. Yeah. Here, I was just calculating, so if this is, if omega equals 10, I was just kind of doing it crummy, but anyway. So if omega equals 10 and omega equals 2 pi f and 10 equals 6.3, 6.2 pi, is 6.3? 6.3, I'm sorry, 6.3 f, so f equals 10 over 6.3. Yeah, 16.8, 6.3. Pi is 1.314, right? Okey-doke. Any other questions? So we use the same thing to design really good bandpass amplifiers. Here's an example of a bandpass. So basically, we have a high pass and a low pass filter, which we can characterize by the same technique that we just described. So basically, we get kind of a closed loop, gain function. And so, the closed loop gain function for this particular circuit is this. That's a closed loop. Okay. And it'll have basically a pole and tell you exactly where the breakpoints are. So it'll give you a frequency response that looks something like this. This is something that we do all the time to build instrumentation. So I can propose to you that if we have this circuit right here, and if I give you some design constraints, you should be able to pick out what R1, C1, R2, and C2 are. And so if I tell you, for example, that I want my system, for example, to have a bandpass from 10 to the 3 radians to 10 to the 4th, I want it to roll off at each of those points at 20 dB per decade. And I also tell you that I want the gain midband to be 10. That basically sets the ratio of R. So basically R over Ri gives you the gain at 10, and that gives you the value of the input resistance. And so if I get that ratio, I say R1 equals 10 to the 5th, R2 equals 10 to the 6th. And again, I have to give you one or the other. I can't not specify one. But anyway, that gives you the correct ratio to get the right midband gain. And then I can calculate, go back to the previous equation, and I can calculate the low frequency breakpoint, which is 1 over R1 C1, and the high frequency breakpoint, which is dependent upon the feedback resistance and capacitance. And so given those, I can plug in 10 to the 3rd for the low breakpoint, 10 to the 4th for the high breakpoint, and I already have R1 and R2, so I've calculated that because of the gain function. I already told you how to do that, and so that gives you the value of the capacitance. And so this is an example that you should be able to do. This is a very good circuit to remember. This is a bandpass amplifier. And anything you do in biomedical engineering, whether it's measuring electrocardiograms or EEG or proteins in a test chamber or whatever, you need to have an amplifier. This is how you build a bandpass amplifier. And you can do it knowing the principles of negative feedback. Any questions? Yeah.
So if we gave us an example like this, would we have to derive the formula for the gain? Would we have to know how to do that?
I don't. So, how do you get this? Is the question.
Yeah.
So, it's not hard. This is Zi, and this is Zf. And so, Zi equals R1 plus 1 over SC1. And Zf is going to be the parallel combination So it's going to be R2 1 over SC2 divided by R2 plus 1 over SC2. So you should be able to get that. You should be able to derive that easily. So all you have to do is plug that into the, so the closed loop gain, GC is just ZF over ZI, right? You should be able to do that. Now, you don't have to memorize that equation, but you should know how to get to it. Any other questions? So one of the things that's important is that as biomedical engineers, you may get called on to design a proportional integral derivative controller. We do this all the time. So our body does it. You know, we have, I just showed you how the cerebellum, we can write an equation for the cerebellum, closed loop equation. Well, you may be called upon to build a blood warmer, for example, in the lab. And your specifications are going to be that I need to keep the blood between the temperature of 37 degrees and 38 degrees, and I have a very high penalty that everything goes over 43 because it'll likes the red blood cells. And so you may have the occasion somewhere in your biomedical engineering career to use a proportional integral derivative controller to do something in the lab. So you can go online, and Texas Instruments makes these Freescale, used to make them. There are a number of different companies, but you can buy these. You actually buy a package, which is usually a development package. And so in that development package, you get the chip along with the programmable board, and you get the software to be able to program your controller so that if you put in an analog input, you will get a desired analog output. Now the controller itself is going to be all digital. So inside this,